Okay, before we start, just a short schedule update. So there are now short talks scheduled for Thursday and Friday morning. Also, it seems like it would be useful to have a group discussion optional. Attendance won't be taken. Tomorrow afternoon, at 2, people are filtering away Friday afternoon, so tomorrow afternoon at 2, what did I learn at the KITP discussion? So with Lenny as the moderator.
This is to help us fill in our reports, right?
Yes, help you fill, that's right. So let's start then with Tom.
Okay. So my original plan for this talk was to talk about this paper I call Firewall 2 over here, which was an attempt that Willy Fischler and I made to use an old model of the interior of black holes that he and I and Lenny and Igor Klebanov made up in the 1990s. And then a few weeks before I got here, I got an email from Joe complaining about the paper. And, sort of some of his arguments were of the my approximation is better than your approximation type. And then he said something really interesting. He said, I'm an agnostic about the firewall, but I'm convinced that no model like ADS-CFT or matrix theory tells you anything about the black hole interior. And that sort of threw me. And I started to think about it from what I consider to be my best attempt to make a real general theory of quantum gravity that talks about local questions, which is the model we call holographic spacetime. It's really a class of models. And I started thinking about that, and we had published a previous paper on firewalls based on the holographic spacetime formalism, in which we had tried to solve the Amps paradox, but still within the context that the S matrix in asymptotically flat spacetime would contain the information eventually about the interior. It's just that it doesn't come out as fast as Don Page estimated that it would come out on the basis of genericity of states. And in our models, there's a very clear reason for that, which I'll be telling you about. But as I started thinking about Joe's question, I realized that in our model, I probably agree with Joe. And so one of the big messages of this talk at the end will be that I actually think that within the context of the type of models we're studying, unitarity of the S matrix is compatible with information loss. And that's something that that was meant to bring that look to Don's face. And you'll see how it works. So these are models that are supposed to replace local field theory. And I want to defer all questions about how can these models give us as much as we know about to be true about local field theory to the end of the talk, basically, after I've finished. Because I really want to tell you about the basic ideas behind these models and show you how the dynamics of the models work in a way that I think is pretty convincing ordinary quantum mechanics. And then I'll say some things about how, within this context, to model the experience of an observer inside a large black hole, all the way through the period that the black hole evaporates. So we'll see the word observer is totally ridiculous in this context. And I'll tell you what the right word is to use instead. And then I'll get to the point, or this answer to Joe's query about whether the S matrix contains the information. So let me start by telling you what our basic ideas were. Our basic idea was to use the notion of Einstein locality from quantum field theory plus the holographic principle as formulated most crisply by Raphael Bousso in the following form. Raphael said, if you give me a causal diamond in any Lorentzian spacetime, then that causal diamond on its boundary has a surface of maximum space-like area, and that area divided by 4 should be the entropy of the Hilbert space that describes every experiment or every piece of physics that can be conceived of in that causal diamond. So we wanted to use that as a building block. That was a conjecture. We wanted to use that as a postulate. And then in terms of that, the fundamental thing in our setup is the quantum mechanics of a time-like trajectory. Now, don't ask me in which space-time this is a time-like trajectory, because the whole point is going to be that by thinking about the quantum mechanics of a whole bunch of time-like trajectories, we will build up the notion of space-time. So the basic idea is that you have some time-like trajectory. If I have a time-like trajectory, and I look at some interval of proper time along that time-like trajectory, and then a longer interval and a longer interval and a longer interval, I get a sequence of causal diamonds made by the past and future tips of those intervals on the time-like trajectory. And that sequence of causal diamonds tends to grow in area. Sometimes it can asymptote to a finite value. Sometimes it explodes to infinity at a finite proper time. And sometimes it just grows asymptotically to infinity with the proper time. That's what happens in asymptotically flat spacetimes, and that's what I'm going to be talking about for the remainder of this talk. Those of you who are so in love with ADS that you can't think about asymptotically flat spacetime, I'm sorry, I can't satisfy your curiosity about ADS here. I don't understand it as well. Yes, definitely. Absolutely, definitely. Okay. So the basic idea is there's some sequence of causal diamonds. There's a particular sequence. Asymptotically flat spacetime is time symmetric, so it's convenient to take time symmetric causal diamonds around some plane of time symmetry. And I think about the unitary transformation in the quantum mechanics that takes me from minus Tn to plus Tn, where Tn gets bigger and bigger as I go out from the center of that diagram. If I think in more conventional terms, in terms of history, I'm coming in from the past. There's a Hamiltonian Hn at each time, which tells me how to go to the next time inward, or also, because of time symmetry, how to proceed forward from the future of causal diamond n to causal diamond n plus 1, or I guess I said n minus 1 to n in this formula. Causality is imposed on this formalism by saying the following thing. There's some big Hilbert space in which this all happens. That's the Hilbert space of the biggest causal diamond on the picture. Let me associate this with a time capital N. Capital N is an integer. It's a time in Planck units. And I want to take it larger than the evaporation of any black hole, evaporation times of any black holes that we happen to discuss in the course of the lecture. I'm not going to take it to infinity just because the mathematics has the idea of factorizing an infinite dimensional Hilbert space, which you guys do all the time, is very, very fraught with difficulties. And I claim that in the theory of quantum gravity, it's really irrelevant if we believe that there's some meaning at all to finite time propagation. Because in anything like asymptotically flat spacetime, the holographic principle tells us at finite times we only have a finite dimensional Hilbert space to deal with. Now in ADS that's not right. That's one of the reasons it's so hard to understand local physics in ADS, in my opinion. Okay, so what's the fundamental causality principle? It's that at any time t, Hn is equal to Hn in plus Hn out, where Hn in and Hn out act on commuting degrees of freedom, or said another way, the Hilbert space splits into a tensor product of the states that are there in a small causal diamond and states that are space-like with respect to that causal diamond. And the fundamental assumption of causality is that operators in the space-like regions commute with the ones inside, and causality says that the Hamiltonian on the inside should only depend on the variables on the inside. Okay? So as a consequence of that, Hn has to be n-dependent, because the split between inside and outside changes as you go along the trajectory. And this should not shock anybody, because we're not talking about some fundamental time at the boundary. We know in general relativity conservation laws that the Hamiltonian is defined as a surface term at the boundary, and you don't see the boundary anywhere in this picture. Okay? So there's nothing wrong with time dependence as long as somehow in the asymptotic limit I get a conserved time-independent Hamiltonian. Okay. That's going to be absolutely key in the entire discussion. Well, in asymptotically flat spacetime, there's a Poincare group, and there's an H. I'm not talking about that H. Oh, no, I'm not saying that it's true in every spacetime. In spacetimes with asymptotic symmetries, and I said at the beginning, I'm only talking about that case. Though I will get a chance to mention de Sitter at a certain point. Okay, so good. That's a start. Now let me tell you what the variables of holographic spacetime are. The variables are defined in quite a general way as follows. The holographic screen of any causal diamond is a compact Euclidean manifold. Take the Dirac operator on that Euclidean manifold and put some kind of cutoff on its spectrum. What the cutoff is going to depend on the manifold you're talking about. It has to do with the geometry of the holographic screen. And that gives me a finite set of variables for which I postulate commutation relations that have a realization in a finite dimensional Hilbert space. Let me tell you what I'm going to use in the following lecture. I'm going to be thinking, just for definiteness, because I don't think any of my arguments depend on this, but just for definiteness, I want to think about a maximally supersymmetric compactification of M theory, 11-dimensional supergravity, on a very small torus, the smallest torus that possibly exists, such that there are only a few bits of information associated with the internal geometry of the torus. And that's something that may bother a lot of you who think about string theory. Let's also leave that discussion to the end. There are only a few bits of information. Then what happens is that the variables look as follows. There are a bunch of variables psi ia, where this is an n by n plus 1 matrix, little n, by little n plus 1 matrix. And psi dagger bj, which is the conjugate of that, which I write as an n plus 1 by n matrix. And then there are a few of these for each value of those indices. The p values are telling me about the information that has to do with this torus. And they're just a finite number. I'm not going to talk about them anymore. These variables are quantized as fermions. Psi ia, psi dagger bj equals delta ij delta ab. Okay? And there's some p dependence in the story, but basically they're all fermions. So what is n? N is the radius of the holographic screen in Planck units. Okay? And again, because of the torus, precisely what I mean by Planck units is ambiguous by a small finite factor, whether it's the 11-dimensional Planck scale or the 4-dimensional Planck scale. But I've deliberately chosen this case so that there's no issue associated with that. What? No. Sorry? The holographic screen is a two-sphere, okay? And little n is defined with respect to any one of these causal diamonds. And for that causal diamond, I have variables like this, where the index runs from 1 to little n. The whole Hilbert space has the index running from 1 to big N, okay? The counting obviously gives you, if I quantize these things as fermions, something that scales like the area of the holographic screen, okay? So that's what these variables are. Now I'm going to write the Hamiltonian, and I'm only going to write H in of n. I put the n in here so that I could put the in down there. I've changed, n used to be an index. H in of n has the following form. It's an operator I'll call P naught plus 1 over little n squared times the trace, well, it's a sum of traces, sum over k, gk, these things depend on little n in principle, times the trace of psi dagger to the kth power, okay? And this sum k goes from 1 to p, where p is some number. I don't know how big it has to be, but I definitely want to keep it finite and independent of n. Okay? So it might be it might turn out that for purposes of satisfying all the consistency conditions, I'll tell you about, I have to take p equal to 200,000. Okay? But it's fixed, and little n gets very, very big, and big N is finite, but you should think of it as almost infinite. Okay? So that's what the Hamiltonian is. No, this is the model, except that I'm not going to tell you what the GKs are, and they're highly constrained, and I don't know how to satisfy all the constraints. I'll tell you about the constraints in a minute. Yep. Yes. Yeah. Well, no. I mean, the Hilbert space is always the same size. It's this H in which is acting on smaller tensor factors. The Hilbert space is always the same size. There's an H out that I have not told you about yet. Okay? I will tell you constraints on H out in a minute.
Well, my question is very simple. If you go from one surface to the next surface, you lose information.
Absolutely. Right. So if I put in a pure state at the boundary, definitely there's going to be a mixed state at finite times in the in part of the Hilbert space. Okay? But I can tell you how mixed states propagate if I tell you how pure states propagate. So the out part of the Hilbert space always purifies the in part. Okay? And eventually, we will have a formula for H out. I just don't know it yet because it comes from satisfying a whole set of constraints that I'm about to tell you about. Yeah, and I'll tell you why I think that. Okay, so in principle, there's a set of psi's that where I runs from 1 to capital N and A runs from 1 to capital N plus 1, but the Hamiltonian H in of little n depends on only the first little n of these in some way of arranging the counting. Notice that this interaction I've written down so far, at any given n, it doesn't know about how to arrange the indices. It has a huge symmetry group, un cross un, acting on the two. It's really u little n cross u little n plus 1, acting on the two indices. Okay? Now, here's the crucial thing. Well, let me tell you, there are two important issues. This is the Hamiltonian for one particular trajectory in asymptotically flat spacetime. Which one? Well, this particular Hamiltonian is appropriate for some geodesic. All right? Written in the frame where that geodesic thinks it's static. Okay? So that's what n is the time in that frame. There are lots of other geodesics, not to mention other kinds of time-like curves. I have to, according to my own rules, invent a Hamiltonian for all of those other geodesics, and in addition, for any two geodesics or any two time-like curves at any time that I consider simultaneous along the two curves, there are causal diamonds which might overlap. Part of the specification of the dynamics of this system is to give you a time-dependent Hamiltonian for every geodesic, at least in some finely enough spaced lattice of geodesics. I don't want to get into the details of that, but it's not really terribly important. But the important point is, if you just think about the space-time, there are many cases where at some time two geodesics will have causal diamonds that have an overlap. And at that time, there is inside that overlap a maximal size causal diamond. And there's a condition that we impose that says that on that tensor factor of the Hilbert space, which can be viewed in two different ways, there's, of course, a density matrix. And that density matrix, up to a unitary transformation, has to be the same for every two pairs of geodesics. There might even be further conditions, thinking about triple overlaps. In all the explicit models we've actually been able to solve, our ansatz solved all possible multiple overlap conditions as well. So I don't know if that's because you don't need the multiple overlap conditions, they somehow get satisfied automatically, or just because the models I studied are so simple. This is not one of the simple models. I don't know the answer to the question of how many multiple overlap conditions you need. Yes?
Is there a sort of reconstruction statement that if you have the bigger Hilbert spaces and they have overlaps that you specify, that you can then reconstruct a bigger Hilbert space that incorporates both of them, or reconstruct the states in the space that
incorporates both of the two of them? Absolutely not.
Okay, so there's all right.
Okay. So I've been told by various people that what we invented here back in 2003 or so is what's now called strong complementarity. I don't know if that's right or not, but some people in the audience have said that to me. This is the sense in which different observers in this formalism communicate with each other. These constraints are incredibly complicated and strong. And in particular, if you have interesting local physics going on, particle scattering, and you have to say, well, this particle is in this causal diamond now, but a little later on it's going to be in that causal diamond there, then really trying to think about how to satisfy the constraints gets really complicated, and I don't know how to do it. Now, one of the things...
You have some reason to believe that they can be satisfied.
Well, we have models of cosmology where they are definitely satisfied. No. In quantum field theory... Yeah, well, that's the issue. Okay, no, but it's really a serious issue, because if you try to even define these kinds of Hamiltonians for trajectories in quantum field theory, where you have to cut off integrals over the stress tensor with sharp boundaries, then you run into disasters. The ability to do this really in quantum field theory is not possible. You can do it sort of in lattice quantum field theory. In lattice quantum field theory, I think you can talk about this, but then you have the issue that of what, you don't have Lorentz invariance, so what do you mean by the speed of light? What's a causal diamond? Blah, blah, blah. Yeah, right.
But I'm specifically asking whether these conditions appear to be compatible with your large symmetry for your interaction. I might have thought that symmetry, because it clearly doesn't know which of the variables live where in your causal diamond, I might have thought that it would kind of, trying to enforce compatibility between these two regions would violate monogamy of entanglement or something like that.
No, I don't think that that's true. I certainly have models in which it's not true, but I will agree, because we don't have any local excitations in those models, that some of the questions are a lot easier to solve in those models. Okay, now I want to tell you about how we believe local excitations arise in these models. There's a completely separate question about how local excitations arose in the real universe we live in. Not going to talk about that. We have a paper just recently put on the archive about that, but that's a different story, and I'm not going to get into it. So now there are two things that I'm going to assume about this Hamiltonian. One would follow from a conjecture of Sakino and Susskind, if it's right. If it's wrong, I will just say choose the coefficients, GK, so that it's true for this particular class of things. The Hamiltonian here should be a fast scrambler of these degrees of freedom. Okay? That's a postulate. We're going to use that. Sorry? I refer you to their paper. They said matrix models in general are fast scramblers. I don't know whether it's true. What I'm clear about is that there are some models that certainly are fast scramblers. Sorry, it's a global symmetry of this Hamiltonian. It can't be a gauge symmetry because it gets broken the next step, because you add these new variables which transform under it. So you get a bigger symmetry, but I certainly don't think about projecting out on singlets of that symmetry. Absolutely not. You're going to see that all the real physics of this model depends on not projecting out on singlets. So, yep. Yeah. Sorry? Okay. So this is a very good question. So there's something that guides all of our thoughts on this for at least the last 5 years, which is a paper that was written 20 years ago by Ted Jacobson about the relationship between Einstein's equations and the laws, basically, of hydrodynamics, local thermodynamics. And the way I think about space-time is as something whose curvature and so on express the way information flows around and energy flows around in systems that obey the Bekenstein-Hawking area entropy law for every causal diamond, which is what this model is trying to do. So if I tell you I'm going to write down a model for space-time X, what I mean is, I already know what the hydrodynamics of this model is. Let me try to find a quantum theory that's a real quantum theory that has that hydrodynamics. And so then I have the background space-time geodesics as kind of things I can use. So I'm trying to make models that will coincide with what a classical person would say about those geodesics. Okay. So now here's the crucial point. There's a constraint on initial states that I want to impose. And I impose that constraint only asymptotically. So I'm going to impose it at time capital N, okay? And I will impose it in the past. I will show you that the Hamiltonian preserves a constraint of the same form in the future. I will argue to you that the states that satisfy that constraint can be thought of in terms of particles. Okay? So what's the constraint? That's the constraint for n times k plus L matrix elements, okay, where 1 is much, much less than k and L, which are both much, much less than n. And this constraint is supposed to be imposed only asymptotically at very, very large n. Okay? So let me think about what this Hamiltonian does to states satisfying that constraint. This Hamiltonian has psis and psi daggers in it, and so it can create some fermionic excitations, destroy some fermionic excitations, recreate them, redestroy them. I haven't told you the order of the polynomial here, but it's finite. So what I claim is that because of the structure of the Hamiltonian, that as you go in, it acts on fewer and fewer degrees of freedom, and as you come out again, it starts acting on more and more degrees of freedom. But it has the property that as n is taken in this limit, I can't change k asymptotically. So I can't change of order capital N matrix elements to be non-zero. I can change of order 1. Yeah, sorry. Different k. P. Oh, God. I'm illiterate. Okay, so the K and L tell me how many of these constraints I have on the initial state. The range of indices for which this is true.
So they go from 1 to L?
In some arbitrary listing, the indices, no. I is equal, I'm sorry. There are n squared matrix elements here. Out of those, nk plus L are set equal to 0. But random, the commutation relations don't distinguish between the indices. The part of the Hamiltonian I've told you about doesn't distinguish between the indices. The rest of the Hamiltonian is going to be applied to states satisfying this constraint. No. There are nk plus L pairs of I and A for which the constraint is satisfied. I and A run over different ranges by 1. Their range, one goes from 1 to n, the other goes from 1 to n plus 1. The ones for which it's 0, just choose them randomly. Okay, so you've got a matrix, pick out that many matrix elements, set them equal to 0. I'm just saying there are n squared variables like this. I'm going to take a state that satisfies this equation for this many of those variables. Okay? So with these constraints on n, k, and l. Okay. This is, okay. So I've written this equation here. The Hamiltonian acts both in the past and the future. Okay? I'm just thinking about the past evolution now. Okay? So this is the standard time-ordered product formula. Okay? And I'm thinking about the past part of the evolution. You can think of it as the evolution up the bottom of the causal diamond if you want. And then I have the time-reversed Hamiltonian that goes up the top. So what I claim is that in this evolution, k does not change asymptotically because this is a finite n, capital N independent polynomial. And it doesn't get to act very much on the big Hilbert space where you have lots of degrees of freedom available because it keeps getting smaller and smaller. This quantum number k, which is now an emergent asymptotic conserved quantum number of this system, is what we will identify with the energy from the point of view of the Poincare group at infinity. Okay?
So is there a n to the 3/4 somewhere here?
No.
No. So k and l are, I should think of them as being order 1 or being like order n to the 3/4. That's what I'm trying to get at. I'm talking about all possible particle states. You're talking about what's the maximum entropy I can get in particles. That's a more complicated question. All possible particle states will always satisfy these constraints. The fact that k and l are constrained in such a way that the energy is sufficiently bounded not to make a black hole, that's something that is that we put in, after we understand the dynamics more. It's not something I can state at this kinematic level. So, okay? It's not. But it's something from which space-time global symmetries emerge, as I'll mention in a minute. So now what I want to do is think about I need to erase something. I want to think about the matrix M equals psi dagger. And I want to think about that matrix after I've imposed that constraint. So I'm going to set equal to 0 the matrix elements of that matrix that would be 0 if these state constraints were constraints on operators. And what I claim is you can now break this up So the sum of these k sub i's is equal to k. The sum I not equal to j of k sub I, k sub j is equal to L. Okay. And everything else is 0. And by my inequalities, this bottom block is special. It's huge compared to all of the others. Okay? N minus k is still a number of order n. Okay? So now what I'm saying is I told you part of what the information in this state is. An additional constraint on the initial state is that the initial state is a tensor product of a state
involving these non-zero variables and a state involving these non-zero variables. The Hilbert space is obviously a tensor product, and I'm saying in this basis, the initial state is a tensor product. Okay? That's a constraint. That's what I define as meaning particle. Now, one of the things I want you to understand, most importantly for the firewall problem, is that this definition of particle says that if I look at a typical causal diamond, most of the states in the causal diamond are not particles. And if I say I've got particles, even in Minkowski space, then I put an extremely strong constraint on my Hilbert space. I don't have much of the entropy. I'm missing an entropy in leading order in large n times k. All right? This is perhaps a point to mention de Sitter space. In our model of de Sitter space, what we would do is take this same system, except we would just stop n at capital N, a fixed number, and let the system evolve with the h of capital N Hamiltonian for the rest of time. That's the causal structure of de Sitter space as viewed from the proper time of a time-like geodesic. What would happen then is the following. I would find that my initial states are very improbable, and they're very improbable by an amount that's given by n times k. In other words, the probability of finding an initial state with energy k is e to the minus n times k. N is the proportional to the de Sitter radius. So this is an explanation for the de Sitter temperature. How? Well, I told you this Hamiltonian is assumed to be fast scrambling. If I let it go on forever acting on the same set of degrees of freedom, eventually they'll get completely mixed. And the density matrix will be random, maximally uncertain. And then if I ask, among the states that the system has now gotten into, what will be the chance that I find energy E by my definition of energy? It's e to the minus E over KT. Yes.
So Steve has had it first. You should.
Okay, Steve.
Well, so if I have a given region of space or space-time, I might have thought that the huge number of states comes from making something like a black hole that sort of fits that
Yeah,
volume.
but we know that that's wrong in de Sitter space.
Well, okay, but let's think about flat space.
Sorry?
Let's think of, you're describing something that has Minkowski boundary conditions. So again, if I had a region...
I absolutely agree with you.
So is this related somehow to those states in an identifiable way?
Yeah, let me answer your question, but let me first take Don's because it might be related. It's fine. I'm going to answer you. But
I'm confused about the greater than signs and your story about de Sitter space. I mean, and maybe it's trying to understand what you mean by particle, but if you want this to explain the de Sitter temperature, if I have de Sitter space, say the static patch thereof, and I want to know the probability that there is one particle present, it's pretty high. It's roughly a half according to conventional quantum field theory and curved space-time. So on the other hand, I thought you just argued that the probability of finding any of your particle states is exponentially small. So I don't
You're talking about particles that have wavelengths of order the de Sitter radius.
Yes.
Yeah, those particles don't exist in this formalism.
Great.
Okay.
So
there are no such things. There are no such things. So let me give. Sorry. I don't think you're going to see a particle with wavelength of order the de Sitter radius. You'll see a thermal fluctuation of a shorter wavelength particle with a suppressed Boltzmann factor. Okay. Okay. So first of all, A, by this identification, K is actually measuring energy in Planck units. So if K is an integer, I'm really talking about Planck mass particles. And I haven't yet told you how particles come out of this, so you might worry that I've only got particles of Planck mass or bigger. And I think the answer to that is no, but I have to do some explaining. But let me, no, I'm sorry, go on. Oh, these are going to turn out to be massless particles. So I shouldn't have used the word mass. This is the energy in a particular rest frame. And the particles that come out of this most naturally are gravitons and so on.
Okay, so for some reason you're getting the tail of the Boltzmann distribution, the exponential part of it.
Yeah,
but
that's
not
right.
The...
That's right. For the de Sitter temperature, yeah. That's a completely different story, and inflation is not de Sitter space. Absolutely not. Read our paper. To come back to Steve's question, this is the key to what Don told us was the big essential question posed by the firewall argument, which I will interpret in my own way. Okay? What Don said is the problem is the finite density of states. And the way I interpret that is, yeah, if I think about a black hole, the black hole in a very tiny interval around its central mass has a huge number of states, the e to the Bekenstein-Hawking entropy. But if I try to describe quantum field theory in a causal diamond near the horizon, I only see one low energy state, the vacuum. All right? Our solution to that problem is in every causal diamond, everywhere, at all times, right here around us with no black holes, there are a huge number of quantum states, all of which have, as you'll see, no energy asymptotically, but those states can couple to the states I call particles, which are the only things that do have energy. Okay? Because how was energy defined? Energy was defined in terms of this constraint. What do I think about the energy of all the states down here? Okay? Well, let me get to that in just a minute, because I haven't told you what P naught is. Okay? Energy will be defined by the Hamiltonian. Okay? But I just tried to show you this form of Hamiltonian has an asymptotic conservation law. Now, so this is the way in which we attempt to address the paradox of where the states are. The states are always there. They're there right here, right now, but we don't couple to them very much because the Hamiltonian along our time-like trajectory for the times we measure has a very large value of n, and so the coupling is very small. We do couple to them, in fact, because as you'll see, all of the interactions between particles can be thought of as coming from interaction with these other degrees of freedom. But you'll have to let me go on if you want me to explain that. So let me go on. Okay, so now there's another essential part of the story which has to do with the question of why I chose the particular variables that I chose. So there's a hand-waving explanation that I always give involving the Cartan-Penrose equation and the holographic principle and things like that. But here's the real reason. It's because it works. If I take these variables, and I take one of these k by k blocks, and I take k very large, it's large, it's much smaller than n, but it's still very large. What I find is that from these variables that transform as spinners on the holographic screen, I can construct in the limit of an infinitely large holographic screen, where the spinor bundle in that limit contains what are called conformal killing spinors, I can construct out of these variables the generators of the super BMS algebra, Q alpha of omega. These are generators that are defined on the sphere, and they satisfy the property that Q alpha of omega anticommutator Q beta dot of omega is equal to a number proportional to k, and I say proportional because I'm taking a limit, and you really should only be talking about ratios of these k's in the limit. Omega is a unit vector, a 3-component unit vector defining a point on the 3-sphere, and these generators satisfy the supersymmetry algebra with this as the momentum. I take the Hamiltonian in the large N limit to be the Hamiltonian that appears on the right-hand side. So I've constructed these generators out of my size. They're bilinear formulas in the size. And I take those bilinears and I put them in the Hamiltonian, one for each block, sum over blocks. Okay? Yeah. Sorry. Yeah, I'm sorry. K sub I, excuse me. And, excuse me, there's an omega sub I. So when I do this, I have to construct. These generators give me all possible spinor-valued functions on the sphere. So in order to get this construction, I have to make things that are localized in a smaller and smaller region as k goes to infinity. And it's the ones that are localized around this particular omega I integrated against the conformal killing spinors that give me this commutation relation. I would prefer to write it this way. So there are some underlying things that have delta function commutation relations, but this is already smeared with the conformal killing spinor. Okay? So what these things say is that the natural variables to parameterize the asymptotic space, they're not quite particles. They're more like particle detectors. They're even better description for those of you who are familiar with particle physics is they're Sturman-Weinberg jet detectors. If I back off from infinity, I can't localize things very much. So the best that I can do is sort of fuzzily localize things in a cone, and I'm picking up all of the energy, momentum, and other quantum numbers that flow out through that cone. And in a real asymptotic limit, I can try to localize that into individual particle trajectories. So particles emerge from this really only in the limit. You're really talking about amplitudes to go from certain energy and quantum number flows to other energy and quantum number flows. Sorry? There is no such thing. I told you what the states are. The states are completely described by the fermion algebra of these size. The state where all the size are equal to 0 is just some particular state in that Hilbert space. It doesn't have any special meaning until I start imposing these constraints. So I'm imposing that size equals 0 for some subset of the things. That's the definition of what particle means. And then from that point on, we can ask about what the other states are doing. Now, how much time do I have left? I have no idea when I started. Okay. Yeah, it's not going to work if you want me to talk about black holes. Okay. I'm sorry. It's sort of 10 years of work, and I'm trying to compress it into an hour. Okay. So let me try to make this as brief as possible. You have to look at these consistency conditions between all the different trajectories. Now, there's something that I won't attempt to try to argue to you, both because I don't have time and because the argument is still a little fuzzy, as it were, which is that I said to you that I chose my initial state to be a tensor product between particles and horizon degrees of freedom. As n goes to infinity in the future, I claim that remains true. Okay? Now, that's a hard thing to swallow at first, except you have to realize that at the intermediate times, particle and horizon degrees of freedom have merged into each other. And what I call a particle, when things come out, remember, this interaction doesn't care, because of the big invariance, about which indices are which. And if I start sending in a bunch of particles from infinity, I'm sending in beams of energy, they use up a certain number of degrees of freedom. And in a small enough causal diamond, I won't be able anymore to say those degrees of freedom are somehow separated into localized stuff. They're going to take up all the degrees of freedom in that causal diamond. So what in that causal diamond do I consider to be the difference between particles and horizon? There is none. And then the system goes out, and asymptotically, again, that I argued to you, separates into things I can separately call particle and horizon. I've defined the energy for you such that everything in that big bottom block of the matrix has zero energy. Okay? Only the particle blocks have energy. And so I get this infinite number of decoupled, in the Hamiltonian sense, zero energy states, which have, some of which have interacted with me, but some of those are the constituents of the particles that I actually emit in the future. So we have an argument based on that and a couple of other arguments. And as Lenny said, Feynman told us, if you've got too many, they're all bad. The upshot of that is we believe strongly that the Hamiltonian the evolution operator will take pure particle states into pure particle states in the asymptotic limit. There's no sense to that claim at finite n, only an approximate sense in which it could be true. So now let me quickly talk about black holes. I said a tensor factor between what I called particles, which are the upper blocks, and variables in the lower block. Yeah, except it's not the same product structure because the value of L changes. And so the size of the lower block has changed, either gotten bigger or gotten smaller. So there are a bunch of what I originally thought of as horizon degrees of freedom, which have become particle degrees of freedom or vice versa in the course of this evolution. But I claim because that separation is flexible in that way, everything that I call particles will just go into a product state. I don't expect you to buy that argument, but let's assume it for what goes forth. Now, let me quickly talk about black holes. As Steve said, thinking about black holes in terms of Penrose diagrams is very bad. Well, it's okay, it's fine, if you think of the right Penrose diagram. The right Penrose diagram looks like this. The asymptotic boundary is Minkowski space. And then somewhere in the middle of Minkowski space, there's this thing, which is a cylinder with shrinking cross-section. And that's the stretched horizon of the formed and evaporated black hole. Okay? And that's the causal structure. That's it. So what bothers me about the other diagram is you put someplace over here at a finite time, you put a stop sign and you say, time stops here. That's crazy. That makes no sense. Actually, it does make some sense, and Willie and I wrote down a way in which it could make sense, but I now believe that way, which is talked about in our first firewall paper, is the wrong way to think about black holes. That's the singularity. So there is no singularity. In addition to that, I don't believe that there's any sense in which one should think in a state-independent fashion about an operator or a trajectory that is inside the black hole stretched horizon. Those trajectories really only exist if the black hole is there. If the black hole is not there, I don't have to talk about them. In our formalism, I get to talk about things trajectory by trajectory. So I have to tell you how to describe a trajectory like this that goes up through the evaporating black hole to infinity. How do I describe it? Well, the Hilbert space of that trajectory can be factorized in the following way. There's a set of states that are associated with the black hole. It's time-like. It's a time-like trajectory everywhere inside a black hole. So it hits the singularity, but I'm going to tell you how to interpret that in a way that doesn't force you to say that time stops. Okay? This is not Finkelstein coordinates. This is a time-like trajectory that goes through into the black hole and hits at a finite time along that trajectory, hits what you call the singularity, or somebody might, and I'm going to tell you what happens to it.
I'm just making the statement R equals 0 is
It's not R equals 0. It's not Schwarzschild coordinates. The singularity looks like that. Time-like trajectories hit it at a finite proper time. Okay? So how do I describe the dynamics in here? The way you describe the dynamics in here is you make the following ansatz for the dynamics of these special black hole trajectories. If the trajectory goes inside the horizon, what does that mean? It means that at some finite time, when it penetrates into the horizon, its Hilbert space factorizes into Hilbert space of the black hole, tensor product, Hilbert space of the rest. Okay? The black hole causal structure is telling you that if I describe this trajectory that's going through the black hole, that trajectory for a time of order the black hole evaporation time should be causally disconnected from the outside. That means that A, its Hilbert space never gets bigger than the black hole. So I'm describing not this whole trajectory, which has a Hilbert space equal to the dimension of the whole thing, but just what's accessed by this piece of the trajectory in here. And the Hamiltonian, I claim, you can say is given by the same Hamiltonian that I've written down, which I just erased a bunch of, but that's true. What I'm saying is that your Hamiltonian does not act on the outside degrees of freedom during this period. That's what I'm saying. You have a Hamiltonian that describes the experiments that you can do, and that Hamiltonian does not involve degrees of freedom that have to do with the outside over this period of time. That's the case for a time of order, the Schwarzschild radius, the evaporation time. In a time of order, the Schwarzschild radius, if I look at this Hamiltonian, and I imagine that my initial state had some particles that had energy and momentum such that they were could still be thought of as particles inside the black hole horizon, then those particles in a time of order, the Schwarzschild time, will start to scramble because of this Hamiltonian. And in a time of order, the scrambling time, the whole system will be scrambled. There will no longer be a description of particles. That's the singularity. For this trajectory, that description persists for a time of order, the evaporation time, except that the Hilbert space is very, very slowly shrinking. So remember, the Hamiltonian's time dependent. So I separate off more and more degrees of freedom and say, oh no, these evolve according to the outside laws of physics. The ones on the inside just go on with a smaller Hilbert space, and they're already scrambled. What happens to an observer that jumps into the black hole? And I hate the word observer. What happens to a trajectory that enters into the stretched horizon of the black hole after the page time? After the page time it enters in, it's got this Hamiltonian, starting from the time that it enters. And it's got, if it had particles in its Hilbert space that were falling along with it, they're described by this. I get particle interactions. They'll be modified initially by the fact that the degrees of freedom that they can interact with are different than what they interacted with when they were just free outside the black hole. But the main thing is the time that it'll take for them to be scrambled is still the scrambling time. There's no firewall. Okay? And none of this makes any difference to anything about the Hawking radiation, or at least to anything about what we know about the Hawking radiation, because the entropy in particle states in any causal diamond, by the definition of particles, is much, much less than the total entropy of the system. So describing the particle states as a decoupled tensor factor for a period of time doesn't affect the thermodynamics one bit. Now, those of you who are in love, and I quite understand it with Bill Unruh and Stephen Hawking's wonderful derivation of Hawking radiation, will say, where is that? And what I will say is, it's not real, okay? And that actually, as Lenny explained to us on Monday, Jacob Bekenstein taught us that black holes radiate. Why he didn't publish it, I don't know. But he proved to us that black holes were thermodynamic systems with a particular relation between energy and entropy. That implies they have a temperature. If you put them in flat space in connection with particles, allow them to communicate with particles, they will radiate according to the Stefan Boltzmann law.
That doesn't get the coefficient, though, right?
Sorry?
The coefficient, the pi's and things? I mean, that...
Absolutely. So things like gray body factors and so on, those have to do with the physics outside the horizon. Okay? I had not described to you, photon-photon scattering via exchange of gravitons yet. That's because it's hard. That's one of the reasons it takes us so long to write our papers. We're dumb, and we don't know how to derive. We now believe we understand how to derive from this formalism in any number of space-time dimensions the scaling law of the large distance Eichenal scattering, Newton's law. All right? We think we can derive it from the appropriate generalization of this Hamiltonian in any number of dimensions, but we don't yet have the coefficients, right? We don't have the G Newton M1 times M2 type stuff. So it's hard. That's physics we don't yet know how to do. It doesn't have anything to do with the essential issue of this conference. Okay? It has to do with scattering of particles in space-time. And I mean, the great defect of our formalism is that it's so hard to access that problem. And I freely admit it. I feel myself totally culpable. I only invite some of you to try to do better. Okay? So let me finally come back to Joe's point. Now, maybe you can see what the issue is with Joe's point. As I describe the Hilbert space of these kinds of systems to you, the Hilbert space at infinity factorizes in this very funny way where the factorization changes from initial to final state into these two pieces that I call particles and horizon states. The evolution operator is unitary. I showed you what the Hamiltonian is. It's unitary. Finite dimensions, we don't have any problems with this not being a unitary operator. If my claim is correct that that unitary operator factorizes into U particle of infinity minus infinity tensor U horizon of infinity minus infinity. Okay? Notice that factorization can't be true at finite time, but it might well be true at infinite time. Now, think about my description of the observer inside the black hole. That involved a different tensor factorization of the same Hilbert space. The whole evolution of the whole system from that observer's point of view from minus infinity to infinity is unitary. But the part of his Hilbert space that knew about what happened during the finite time that the black hole existed is some tensor factor. And out at infinity, there's this other tensor factorization into final particles times final horizon. Why should it be the same tensor factor, especially since the horizon tensor factor is so much larger than the particle tensor factor? So I believe that quantum models of this type with asymptotically decoupled time-dependent Hamiltonians, asymptotically decoupled zero-energy degrees of freedom can give us both exact unitarity and information loss. And let me stop there.
People can feel free to go get lunch. Questions go on as long as people have questions.
Yeah. No, so there are a couple of things wrong with the way that you said it. So really, the particle degrees of freedom are a subset of the horizon degrees of freedom. So the total set of degrees of freedom are just these fermionic size, fermionic matrices. If I put a certain constraint on the Hilbert space, I can interpret a subfactor of that Hilbert space in terms of particles, and there are many different factorizations like that, depending on what the incoming particle state is. And what I tried to argue to you is that this quantum system, first of all, it manifestly, by my construction, has the property that any states that I don't call particles have zero energy asymptotically. Second, and this is the hard part, I've claimed that the infinite time evolution operator refactorizes on things that I can call particles times things that I can call horizon in a way that leaves the particle evolution operator from minus infinity to infinity unitary by itself. That's the hard part. We have arguments for that. I'm not, if I had a quick and dirty convincing argument for that, I would give it to you. But it would take a while to tell you all the things I think about that problem. Very good. Okay. Yeah. So I think that there is, and the general condition is one that cannot be encapsulated in any simple cutoff prescription on quantum field theory. That's why I think that although I've indulged in attempts like this, that attempts to construct local quantum fields from string theory have problems. Okay? I've sort of known about this since we worked on matrix theory back in the 1990s, because I spent a couple of years of my life trying to derive local quantum field theory from matrix theory and failed totally. Here, what's going on is the following. When I talk about particle states, what I have, you'll excuse me, I can't draw to save my ass, but okay, that's a sphere, okay? So when I talk about particle states, what I mean is there are little regions on the sphere, and region is defined by these variables psi. These psi's are effectively functions on the sphere. They're spherical harmonics, and I make sums of them, which are somewhat localized in regions. That's what I'm talking about when I talk about regions. And particle states are such that I can isolate these things that have to do with small finite regions on the sphere, and most of the entropy of all the degrees of freedom on the sphere has been gotten rid of by putting on one of these constraints. That's what a particle state is, asymptotically at the very last, detector out at infinity. A real particle is, of course, not this detector element, but it's a track that I follow in through many causal diamonds. And when I start doing that, I suddenly, at some point, if I've got a bunch of particles, and I have a particular trajectory which is such that in a small causal diamond of that trajectory, all of these particles get in there, at a certain point, they're going to fill up the sphere. That detector doesn't have that many degrees of freedom anymore. It's not a sphere, really. It's a fuzzy sphere. It's only got a finite number of angular momentum components, smaller number as the proper time gets smaller. At that point, some terrible interaction occurs. If that region is big enough, macroscopically large, much, much larger than the Planck scale, that event is called formation of a black hole. If it's really, really small, then it's called an interaction between particles. And then you look at what happens as you go out in the future to bigger causal diamonds, and you again, in the larger causal diamonds, are able to isolate out little regions like this that carry energy. Okay. So one of the things that you could take as a slogan, but as Steve said, don't take this seriously, is that in this model, all interactions between particles are mediated by the formation and evaporation of tiny black holes. And
I don't actually want to cut off questions, but I think people are probably about to faint from hunger. So
I'm one of those people. So.